There are 3 facts buried in the mathematics of the last century that, taken together, should have rewritten every engineering textbook and every financial model on Earth. Why did the most famous mathematician in France pay more than his own prize money in 1889 to destroy every printed copy of his award-winning paper before anyone could read it? What does a suspension bridge in Washington state have in common with the emergency shutdown button inside Chernobyl Reactor 4? And why is Mercury, right now, tonight, still in a stable orbit only because Albert Einstein happened to be correct about a correction to gravity that nobody at the time thought mattered? These 3 questions have the same answer. It is a mathematical result, discovered by accident in 1961, when a meteorologist at MIT went to get a cup of coffee and came back to find that the future of an entire simulated planet had changed because he rounded one number from 6 decimal places to 3. That result says every stable system you have ever depended on contains somewhere inside itself a hidden feedback loop that, given enough time, will find its way to the surface and tear the system apart. It was published in 1963. It was confirmed as a universal law of nature in 1978. And the institutions that design your bridges, manage your power grids, and model your climate have spent 60 years acknowledging this result in technical papers and then continuing to operate as if it does not apply to them. Tonight, we are going from Poincaré's destroyed memoir, to Lorenz's rounding error, to Feigenbaum's rejected paper, to the 4 minutes that blacked out 55 million people, to Laska's simulations of Mercury crashing into the sun, to the feedback loops already running in the Arctic permafrost, to a question about the architecture of the universe itself that nobody has been willing to ask out loud. Get comfortable, and if you have not already, subscribe or join. If you want more of this across physics, math, and the hidden structures holding reality together, the Patreon goes deeper across all of it. Stay to the end of this one, because the final implication, the one that connects a meteorologist's rounding error to the vacuum state of the Higgs field, is the part that should keep you up tonight. Let's go back to where this began. On August 14th, 2003, at 4:06 in the afternoon, the largest power grid in North America began to eat itself. It started with a tree branch in Ohio. A single transmission line sagged into an overgrown tree in the yard of a First Energy substation outside Cleveland, and the line tripped. That should have been nothing. Power grids are built to absorb the loss of a single line, the way your body absorbs a paper cut. Automatic systems reroute. Neighboring lines pick up the slack. The lights stay on. But at 4:06, the lights did not stay on because something had already gone wrong 3 hours earlier that nobody knew about. A software bug, a race condition in a GEXA-21 energy management system, had quietly crashed the monitoring computers at First Energy's control center. The operators had been flying blind since 2:14 that afternoon. They did not know the first line had tripped. They did not know the second line had tripped 12 minutes later. They did not know the third line tripped at 3:41. By the time the fourth line went down, the remaining lines in the region were carrying more current than they were designed for, and current generates heat, and heat makes metal expand, and expanding metal makes lines sag, and sagging lines hit trees, and hitting trees trips more lines, and tripping lines pushes more current onto the survivors. 4 minutes. That is how long the cascade took, from 4:06 to 4:10. 508 generating units at 265 power plants tripped offline in a sequence so fast that no human being could have intervened even if they had known what was happening. 55 million people across Ontario and 8 American states went dark. 11 people died. The estimated damage was $6 billion, and the entire thing was caused by the interaction of a software bug, a tree branch, and a mathematical principle that had been discovered 42 years earlier by a meteorologist who went to get a cup of coffee. That principle does not have a name you would recognize. It is not a single equation you can point to on a blackboard. It is more like a structural fact about the universe, a fact so fundamental and so uncomfortable that the scientific establishment spent the better part of 2 decades pretending it did not exist, after it was first demonstrated. And the fact is this: every system that appears stable, every bridge that stands, every grid that holds, every market that functions, every orbit that repeats, every climate that persists, contains somewhere inside itself a hidden coupling between its own output and its own input, a feedback loop. And that feedback loop, given enough time or the right perturbation, will find its way to the surface. When it does, the system does not degrade. It does not slowly wind down. It tears itself apart on a timescale that makes intervention impossible. The mathematics behind this was discovered accidentally in January of 1961 by a man named Edward Lorenz at MIT. It was published in 1963 in a paper that received exactly 3 citations outside of meteorology in its first decade. It was independently confirmed in 1978 by a physicist whose paper was rejected twice before anyone would print it. And the implications, the full implications, the ones that extend from weather patterns to nuclear reactors, to the orbit of Mercury, to the vacuum state of the universe itself, have still not been publicly reckoned with by the institutions that depend most on the assumption that stability is the natural state of things. That assumption is wrong, and the people who know it is wrong have known for over 60 years. I want to be precise about what I mean by that, because this is not a metaphor. This is not a philosophical argument about impermanence or a poetic observation about the fragility of human systems. This is a mathematical result. It has been proved. It has been experimentally confirmed. It shows up in fluid dynamics, in orbital mechanics, in ecology, in cardiology, in economics, in neuroscience, in the behavior of dripping faucets. And it says that the thing you experience as stability, the solid ground you are standing on, the predictable sunrise, the market that opens every morning, the climate that has sustained human civilization for 10,000 years, is not a permanent condition. It is a temporary phase. A system that looks stable is a system that has not yet found its bifurcation point. And every system, given the right mathematics, has one. But here is the part that should genuinely disturb you. The reason this result sat in obscurity for over a decade after it was published has nothing to do with its validity. Nobody disputed the math. Nobody found an error. The reason it was ignored is that it contradicted a belief so deeply embedded in Western science, so central to the operating assumptions of every institution from NASA to the Federal Reserve, that accepting it would have required rebuilding the conceptual foundations of prediction itself. That belief is the Newtonian premise, the idea that if you know the initial conditions of a system precisely enough, and you know the laws governing that system, you can predict its future state to any degree of accuracy you want. Lorenz proved that this is false, not approximately false, not false for certain special cases, structurally false for any system with nonlinear feedback, which is virtually every real system in the universe. The precision of your initial conditions does not matter. The error will find a way to grow, and it will grow exponentially on a timescale determined by the system's own internal dynamics, until your prediction is worthless. That is not a limitation of our instruments. That is not a problem we can solve with better data or faster computers. That is a property of the mathematics itself. And the fact that you were never told this, that this result has been public knowledge since 1963, and yet the dominant cultural narrative about science still runs on the Newtonian assumption that prediction is limited only by measurement, should make you angry, because the people who design your bridges, who manage your power grids, who model your climate, who trade your retirement savings, are building on a foundation that a quiet meteorologist at MIT proved was cracked 60 years ago. The story of how he proved it starts with a cup of coffee and a rounding error. But before we get there, I need to take you back further, because Lorenz was not the first person to discover this. He was the first person to demonstrate it with a computer. The actual discovery happened in 1889, and it was so disturbing that the man who made it paid out of his own pocket to destroy every copy of the paper before it could be distributed. That man was Henri Poincaré, and what he found hiding in the mathematics of the solar system is the reason you should not sleep well tonight. In 1885, King Oscar II of Sweden announced a prize competition to celebrate his 60th birthday. The prize was 2,500 Swedish kronor and a gold medal, and the question was deceptively simple. Prove that the solar system is stable. Show mathematically that the planets will continue in their orbits forever, that the clockwork Newtonian universe actually works the way everyone believed it worked. The deadline was June 1st, 1888. The judges were three of the most prominent mathematicians in Europe, and the prize was widely understood to be a formality. Everyone knew the solar system was stable. Newton had shown how it worked. Laplace had refined the calculations. The question was not whether stability could be proved, but who would write the most elegant proof. Henri Poincaré was 34 years old when he submitted his entry. He was already regarded as one of the finest mathematicians of his generation, a professor at the Sorbonne with an almost unsettling ability to hold entire mathematical structures in his head without writing them down. His submission focused on a simplified version of the problem, the restricted three-body problem, in which two massive bodies orbit each other and a third body of negligible mass moves in their gravitational field. He did not prove stability. What he proved instead was something far more important and far more dangerous. His memoir was awarded the prize on January 21st, 1889. The gold medal was struck. The paper was typeset in Acta Mathematica, volume 13, ready for distribution. And then the editor, Lars Edvard Fragman, started asking questions. Detailed, persistent, technical questions about certain passages in the proof that seemed to skip steps. Poincaré initially tried to address the queries with clarifications, but as he dug deeper into his own calculations, he found something that made him send an urgent telegram to Gösta Leffler, the journal's editor, on November 30th, 1889. The telegram said to stop the presses. What Poincaré had found was an error, not a minor error, a structural error that, when corrected, reversed the meaning of his result. His original submission had appeared to show that certain orbits in the three-body problem were well behaved, that small perturbations led to small deviations, that the system stayed close to where it started. The corrected version showed the opposite. Small perturbations could lead to wildly divergent trajectories. Orbits that started nearly identically could end up in completely different regions of phase space. The geometry of the solutions was not smooth and predictable. It was tangled, folded back on itself in structures so complex that Poincaré himself could barely describe them. He later wrote that these structures, which we now call homoclinic tangles, were so complicated that he did not even attempt to draw them. The embarrassment was acute. Poincaré was the most famous mathematician in France. He had won a prize from the King of Sweden for a result that turned out to contain a fundamental error. And the error, when corrected, said the opposite of what everyone wanted to hear. The original version suggested stability. The corrected version proved the possibility of chaos. He could have tried to minimize the damage, to frame the correction as a minor technical adjustment. He did not. He corrected the error honestly and paid the cost, both financial and reputational. The correction cost Poincaré more than the prize. The reprinting bill for recalling and replacing the already distributed copies of the journal exceeded the 2,500 kroner he had won. He paid it out of his own pocket. And the corrected memoir, published in 1890, running to 270 pages in Acta Mathematica, contained the first description in the history of mathematics of what we now call chaos. The first demonstration that a perfectly deterministic system, governed entirely by Newton's laws, with no randomness and no uncertainty in the equations themselves, could produce behavior that was effectively unpredictable. Think about what that means for a moment. Poincaré had set out to prove that the solar system was stable, that the planets would orbit forever in their prescribed paths, that the Newtonian clockwork was sound. And what he found instead was that the mathematics could not make that guarantee. Not because Newton was wrong, not because gravity was more complicated than expected, but because the three-body problem, the simplest possible extension of the two-body problem that Newton had already solved, contained a geometric structure in its solution space that made long-term prediction fundamentally impossible. The solar system you are sitting in right now has 8 major planets, dozens of significant moons, and thousands of gravitationally relevant minor bodies. Poincaré could not even prove stability for 3. And that result, published in 1890, was buried, not suppressed by any conspiracy, buried by indifference, by the mathematical community's collective decision that this was a pathology, a curiosity, a gallery of monsters, as one mathematician later called it, rather than a fundamental truth about the universe. It took more than a century for someone to finish the job Poincaré started. In 2009, Jacques Lascar and Mikhail Gastineau at the Institut de Mécanique, Céleste et de Calcul des Éphémérides in Paris, published a paper in Nature that should have been front-page news around the world. They had run 2,501 simulations of the solar system's future, integrating the full gravitational interactions of all the planets, including general relativistic corrections and the gravitational influence of the Moon, using the JD supercomputer. Each simulation ran for 5 billion years. And the result was this. In approximately 1% of those simulations, Mercury's orbit became unstable. Its eccentricity climbed past 0.7, and the planet either fell into the Sun or collided with Venus. 1% might sound small, but you need to understand what Lasker found underneath that number. Without Einstein, without general relativity, the probability of Mercury's orbit going catastrophically unstable jumps from 1% to more than 60%. The only reason Mercury is still in a stable orbit right now, the only reason the inner solar system has not already torn itself apart, is that Einstein's correction to Newtonian gravity, the same 43 arc-seconds per century of perihelion precession that confirmed general relativity in 1915, detunes a resonance between Mercury's orbital frequency and Jupiter's. That resonance, if it were not damped by the relativistic correction, would pump Mercury's eccentricity higher and higher with each orbit, like pushing a child on a swing at exactly the right moment. A positive feedback loop between the two planets, hidden in the gravitational mathematics, held in check by a correction to Newton's equations that Newton himself could never have known about. The solar system is not a clockwork. It is a chaotic system with a Lyapunov time of approximately 5 million years. That means that if you made a copy of the solar system right now, identical in every way except that you moved one asteroid by 1 millimeter, the two copies would diverge so completely within about 5 million years that you could not tell which was which. 5 million years sounds like a long time. It is not. The Earth is 4.5 billion years old. It has already lived through roughly 900 Lyapunov times, 900 complete reshufflings of the sensitivity dice. The fact that it has survived this long is not evidence that it will continue to survive. It is a statistical statement about the current configuration of the planets, a configuration that Laska's simulations show has a finite, calculable, non-zero probability of failing. This is not speculation. This is not theoretical. This was published in Nature in 2009. The paper has a DOI number. You can look it up. And the fact that you almost certainly have never heard of it, that this result did not reshape public discourse about the nature of the universe, is itself a piece of evidence about how institutional science handles truths that are too uncomfortable to integrate. The solar system is unstable, not in some abstract philosophical sense. In the hard, numerical, we ran 2,501 simulations, and here is the distribution of outcomes sense. And the mechanism that makes it unstable is the same mechanism that crashed the power grid in 2003, the same mechanism that melted the core at Chernobyl, the same mechanism that a meteorologist at MIT found hiding inside a weather simulation in January of 1961. But the 1961 discovery is worse than the solar system result, because Lorenz did not just find that one particular system was unstable. He found something universal, something that applies to every nonlinear system with feedback. And he found it by accident, because he went to get a cup of coffee. Edward Norton Lorenz was born on May 23, 1917, in West Hartford, Connecticut. His father was an MIT-trained mechanical engineer. His mother was a direct descendant of the Puritan settlers of New England. He grew up solving puzzles. As a child, he memorized the positions of the stars. He could recite the cloud classifications before he was 10. He went to Dartmouth for his undergraduate degree in mathematics in 1938, then to Harvard for a master's in the same subject. And then World War II happened, and the Army Air Corps needed weather forecasters. And Lorenz discovered that the atmosphere was the biggest, most complicated, most beautiful puzzle he had ever encountered. After the war, he went to MIT for a doctorate in meteorology. He joined the faculty in 1948. He became a full professor in 1962. And for the first 13 years of his academic career, he worked on the same problem that had driven meteorology since its founding: long-range weather prediction. Could you forecast the weather 2 weeks out? A month? 6 months? The operating assumption in the field, the assumption that had driven the development of the first numerical weather prediction models by Jules Charny and John von Neumann in the late 1940s, was that the answer was yes. With enough data, enough observations, and a big enough computer, you could extend the forecast horizon indefinitely. The atmosphere, after all, was a physical system governed by the Navier-Stokes equations, by thermodynamics, by conservation of mass and momentum and energy. It obeyed laws. And if you knew the laws, and you knew the initial state, you could predict the future state. That was what laws were for. Lorenz had a computer, not much of one by modern standards, a Royal McBee LGB 30, which was a desk-sized machine built with vacuum tubes and a rotating magnetic drum for memory. It weighed 360 kilograms, It had 4,096 words of internal memory, each 32 bits wide. It was, as one later researcher put it, 1,000 times faster than his desk calculator, but still 1,000,000 times slower than a current laptop. And Lorenz had programmed it with a simplified model of atmospheric convection. 12 variables, 12 equations, representing the bare bones of how air moves when it is heated from below and cooled from above. He was not trying to predict the actual weather. He was trying to understand the structure of weather patterns, the way convection cells form and break and reform. The machine produced its output on a paper printout, a strip of numbers, 6 variables across, printed line by line as the simulation ran. It stored the numbers internally to 6 decimal places, but to save space on the printout, it rounded them to 3, 6 digits in the machine, 3 digits on the paper. In January of 1961, Lorenz was running one of these simulations and saw something interesting partway through the output. He wanted to look at it more closely, to run the simulation again from that point and watch how the pattern developed. So he did what any reasonable person would do. He looked at the printout, found the line of numbers corresponding to the point he wanted, typed those 3 decimal place values back into the machine, and pressed start. Then he walked down the hall to get a cup of coffee. When he came back roughly an hour later, the computer had simulated about 2 months of weather, and the numbers on the new printout were nothing like the numbers from the original run. Not just slightly different, completely different. The 2 simulations, which had started from what should have been the same initial state, had diverged so far that they described entirely different weather patterns. Lorenz's first thought was that a vacuum tube had failed. Hardware problems were common with the LGP-30, but he checked, and the hardware was fine. So he looked more carefully at the inputs, and he found the discrepancy. He had typed 0.506. The computer's internal value had been 0.506. 127. The difference was less than 1 part in 5,000. It should not have mattered. In any linear system, a tiny error in the initial conditions produces a proportionally tiny error in the output. That is the Newtonian premise. That is how prediction is supposed to work. But Lorenz's weather model was not linear. It contained feedback loops. The output of one equation fed into the input of another, which fed back into the first. And in that tangle of feedbacks, the tiny error did not stay tiny. It grew. And it grew exponentially, doubling and redoubling at a rate determined by the internal structure of the system, until the 2 simulations had nothing in common at all. I want to be very clear about what Lorenz discovered that afternoon. He did not discover that weather is hard to predict. Everyone already knew that. He did not discover that measurements contain errors. That is trivially obvious. What he discovered is that there exists a class of perfectly deterministic systems, systems with no randomness in them whatsoever, governed entirely by fixed equations, that are structurally incapable of being predicted beyond a finite horizon, no matter how precisely you measure their initial state. The error does not just grow. It grows exponentially. And exponential growth in a bounded system means that after a calculable number of time steps, your prediction contains no more information about the actual state of the system than a random guess. That moment, that hour in January of 1961, while Lorenz was drinking coffee and his Royal McBee was grinding through 2 months of simulated weather, is arguably the most important accident in the history of science since Alexander Fleming left a petri dish uncovered in 1928. Fleming's accident gave us penicillin. Lorenz's accident gave us something equally transformative, but far less comfortable. It gave us the mathematical proof that the future is not and cannot be a knowable function of the present. And Lorenz, characteristically, did not panic. He did not rush to publish. He spent the next 2 years working through the implications methodically, reducing his 12-variable weather model to the simplest possible system that still exhibited the same behavior. He found it in a set of 3 coupled ordinary differential equations derived from a 1962 paper by Barry Saltzman on Rayleigh-Bernard convection, the flow pattern that emerges when a thin layer of fluid is heated from below. The 3 variables in Lorenz's reduced system had precise physical meanings. X was proportional to the intensity of the convective motion, the speed at which the fluid circulated. Y was proportional to the temperature difference between the rising and falling currents. Z was proportional to the distortion of the vertical temperature profile from linearity. 3 variables, 3 equations, and in those 3 equations, the entire architecture of chaos. He called this sensitive dependence on initial conditions. In his own words, from his 1993 book, The Essence of Chaos, he defined it as the phenomenon that a small alteration in the state of a dynamical system will cause subsequent states to differ greatly from the states that would have followed without the alteration. He added that sensitive dependence can serve as an acceptable definition of chaos. That sentence, buried in a book published 30 years after the discovery, is one of the most important sentences in the history of science, and almost nobody has read it, because Lorenz did not publish his findings in a physics journal or a mathematics journal. He published them in the Journal of the Atmospheric Sciences, Volume 20, Issue 2, March 1963, pages 130 through 141. The title was Deterministic Non-Periodic Flow. It is a 12-page paper that contains 3 equations, a description of a strange attractor that would later bear his name, and a demonstration that a perfectly deterministic system can produce output that never repeats and can never be predicted. Between 1963 and 1973, that paper received exactly 3 citations from outside the meteorological community. 3. In 10 years. The Lorenz attractor, the geometric object that is 3 equations traced through a mathematical space defined by 3 variables, looks like a butterfly, 2 lobes, 2 wings, connected by a narrow channel. The trajectory loops around one wing some number of times, unpredictably jumps to the other, loops there, jumps back. It never crosses itself. It never repeats. It inhabits a surface with a fractal dimension of approximately 2.06, meaning it is more than a flat plane, but less than a solid volume. The trajectory is infinitely long and occupies 0 volume. It is dense everywhere and hits no point twice. And within this object, 2 trajectories that start arbitrarily close together will diverge exponentially, winding around the wings in completely different sequences after a number of orbits determined by the system's maximal Lyapunov exponent, which for Lorenz's standard parameters is approximately 0.906. If you could watch the Lorenz attractor unfold in real time, you would see something that looks alive. The trajectory spirals around one wing, gaining speed, then slows, hesitates at the narrow channel between the wings, and then, with no apparent cause, jumps to the other wing and begins spiraling there. The jumps are not random. They are completely determined by the equations, but they are sensitive. 2 trajectories starting so close together that you could not tell them apart on any screen would, after a few dozen orbits, be on different wings, at different speeds, at different phases. The attractor is deterministic and unpredictable at the same time. That combination is the essence of chaos. The system obeys laws, but the laws do not produce a predictable outcome. You know the rules, and you still cannot tell what comes next. That is not just a property of simplified weather models. That is a property of your life, the economy you participate in, the traffic patterns you navigate, the weather you check every morning, the relationships you maintain, the career you are building. Every one of these is a nonlinear, dynamical system with feedback. Every one of them is deterministic, governed by causes that produce effects, and every one of them is sensitive to perturbations small enough that you will never see them coming. The rounding error in your career, the tree branch in your financial plan, the software bug in your expectations. The Lyapunov exponent is the key number, named after Alexander Mikhailovich Lyapunov, who introduced it in his 1892 doctoral dissertation at Moscow University. It measures the average exponential rate at which nearby trajectories in a dynamical system diverge over time. A positive, maximal Lyapunov exponent is the mathematical definition of chaos. It means errors grow exponentially. The inverse of the Lyapunov exponent gives you the Lyapunov time, which is the characteristic timescale over which a small error grows by a factor of e, roughly 2.72. For Lorenz's weather model, that timescale was on the order of a day or two. For the real atmosphere, it is similar. For the inner solar system, as I mentioned earlier, it is about 5 million years. For your heartbeat, it is on the order of seconds. The number changes. The mathematics does not. What this means, in practical terms, is that Lorenz had discovered a fundamental limit to prediction, not a limit imposed by our instruments or our computers or our models, a limit imposed by the structure of the equations themselves. Even if you could measure the initial state of the atmosphere to a precision of 1 part in a billion, even if you had a computer the size of the universe running the most perfect model ever devised, the forecast would become useless after about 2 weeks. The error would find a way to grow. It always finds a way to grow. That is not a failure of our methods. That is what the mathematics says must happen. The meteorological community did not want to hear this. Lorenz, as a weather forecaster, had just told his colleagues that the fundamental aspiration of their field, deterministic long-range prediction, was mathematically impossible. Some operational forecasters continued to argue for decades that with sufficient observation density and computational power, the 2-week barrier could be broken. It could not. It has not been. The practical forecast horizon today, more than 60 years after Lorenz's paper, remains at about 10 to 14 days. The response to this limit was not to give up on forecasting, but to shift to ensemble methods, running many slightly different simulations and looking at the distribution of outcomes rather than any single trajectory. That shift was not institutionalized until the 1990s. It took 30 years for the field to accept what Lorenz had proved in 1963. There is a detail about Lorenz that I have not mentioned yet, and it speaks to the kind of person he was. After discovering sensitive dependence on initial conditions, after realizing that long-range weather prediction was fundamentally impossible, Lorenz did not change careers. He did not write a popular book. He did not go on a speaking tour. He went back to his office at MIT, continued studying atmospheric dynamics, and spent the next 4 decades methodically exploring the implications of what he had found. He published papers on the limits of predictability, on the structure of strange attractors, on the differences between the butterfly effect in bounded and unbounded systems. He was not dramatic about it. He was precise. His colleagues remembered him as someone who expressed profound ideas in the fewest possible words. His wife Jane died in 2001. They had been married for over 50 years. He continued hiking, continued working, continued thinking about the atmosphere and the equations that governed it. His final paper was published in 2005, 3 years before his death, at the age of 88. He was still asking new questions about the system he had first encountered on a printout from a vacuum tube computer in 1961. He had not solved the problem of chaos. Nobody has. He had simply proved that the problem exists and then spent his life trying to understand its boundaries. Lorenz himself was characteristically quiet about the implications. His colleagues at MIT described him as reserved, meticulous, and capable of expressing profound ideas in the fewest possible words. Kerry Emanuel called him like a mountain goat. He hiked the White Mountains and the Rockies until 2 weeks before his death. Jewel Charney called him a genius with the soul of an artist. He never won a Nobel Prize because there is no Nobel for mathematics or meteorology. The prizes he did receive came late. The Crafoord Prize in 1983, a prize created specifically to honor disciplines excluded from the Nobels. The Kyoto Prize in 1991, with a citation that said chaos theory had profoundly influenced a wide range of basic sciences and brought about one of the most dramatic changes in mankind's view of nature since Sir Isaac Newton. He died on April 16, 2008, at the age of 90, in his home in Cambridge, Massachusetts. His colleague Kerry Emanuel wrote this in his memorial. By showing that certain deterministic systems have formal predictability limits, Ed put the last nail in the coffin of the Cartesian universe and fomented what some have called the third scientific revolution of the 20th century, following on the heels of relativity and quantum physics. The third scientific revolution. And the man who started it published in a weather journal that nobody outside meteorology bothered to read. But here is where it gets worse, because Lorenz's discovery, as fundamental as it was, left an escape hatch. You could look at what he found and say, fine, weather is unpredictable. Certain chaotic systems are unpredictable. But that does not mean everything is. Maybe chaos is a special case. Maybe it shows up in weather, and in certain fluid dynamics problems, and in a few exotic mathematical models. But the rest of the world, the engineering world, the financial world, the biological world, is better behaved. Maybe stability really is the default, and chaos is the exception. In 1975, a physicist at Los Alamos closed that escape hatch forever, and the scientific establishment rewarded him by refusing to publish his paper for 2 years. Mitchell Feigenbaum was born on December 19, 1944, in Philadelphia, and grew up in Brooklyn, the son of an analytical chemist and a schoolteacher. He was the kind of physicist who could not stop his brain from working, even on things nobody had asked him to think about. He was restless, chain-smoking, often awake until 4 in the morning, prone to wandering off the beaten path of respectable research. After finishing his PhD at MIT in 1970 under Francis Lowe, he moved through a series of positions before landing at Los Alamos National Laboratory in 1974. He was hired to work on problems related to turbulence, the notoriously difficult transition from smooth laminar flow to wild, disordered flow in fluids. But what he ended up working on was simpler and more profound. In the summer and fall of 1975, Feigenbaum was playing with a Hewlett-Packard HP 65 programmable calculator, one of the earliest handheld programmable calculators ever made, a device that cost close to $800 and could store programs of 100 steps. He was studying what happens to a very simple mathematical system, the logistic map, as you turn up a single parameter. The logistic map is this. You take a number between 0 and 1, You multiply it by a parameter r, then by 1 minus the number, and that gives you the next number. You repeat. It is a one-line equation. It fits in a tweet, and it contains within it the entire architecture of how stable systems destroy themselves. When the parameter r is low, the logistic map converges to a single fixed point. It is stable. You start anywhere, and the system settles down to one number and stays there. As you increase r, something happens. At r equals 3, the fixed point becomes unstable, and the system begins to oscillate between two values. It has undergone a period doubling bifurcation. The single fixed point has become a 2-cycle. Increase r further, and the 2-cycle becomes a 4-cycle, then an 8-cycle, then 16. The intervals between successive bifurcations get shorter and shorter, telescoping toward a critical value of r beyond which the system becomes chaotic, meaning it never repeats, never settles down, and is sensitive to initial conditions in exactly the way Lorenz discovered. What Feigenbaum found, punching numbers into his HP 65 late at night in his Los Alamos office, was that the ratios between successive bifurcation intervals converge to a fixed number. The first interval is some size. The second interval is smaller by a specific ratio. The third is smaller by the same ratio. And that ratio, as you go deeper and deeper into the cascade, converges to a number that would become one of the fundamental constants of nonlinear dynamics. 4.669, 201, 609, 102, 990, 671, 85, 320, 382. He calculated it to many digits. He stared at it. He had no idea what it was. Then he did something that changed everything. He switched to a different equation. Instead of the logistic map, he tried the sign map. X sub n plus 1 equals r times the sine of pi times x sub n. A completely different function, different shape, different algebra, different properties. And he ran the same analysis, period doubling bifurcations, converging intervals, ratios. Same number, 4.669, 20. Feigenbaum tried another equation. Same number. Another. Same number. Every smooth, single-humped map he could think of, every function with a single quadratic maximum, produced the same convergence ratio when driven through its period doubling cascade. The number was universal. It did not depend on the specific system. It depended only on the shape of the map at its peak. The second constant he discovered, alpha, approximately 2.50290, governed the ratio of widths of successive bifurcation tines, a geometric shrinking factor for the visual structure of the bifurcation diagram. Together, these two numbers, delta and alpha, defined a universal road to chaos that every smooth unimodal system must follow. Not just the logistic map, not just the sign map. Every system, dripping faucets, convection cells, heart rhythms, predator-prey populations, electronic circuits, chemical reactions, financial markets. If the system has a single humped feedback response, the cascade follows the same mathematical script with the same ratios to the same chaotic endpoint. I need to stop here and make sure the weight of this lands properly. Feigenbaum did not discover that chaos exists. Lorenz had already done that. What Feigenbaum discovered is that the transition from stability to chaos follows a universal law. The road to destruction is the same for all systems. The specific numbers might differ. The specific parameter values where bifurcations occur will be different for different systems. But the ratios converge to the same constants. This means that the phenomenon Lorenz found hiding inside a weather model is not a quirk of weather. It is not a special property of fluid dynamics or atmospheric science. It is a structural feature of feedback itself. Any system with a nonlinear feedback loop and a tunable parameter will, as that parameter is pushed, walk down the same Feigenbaum cascade toward the same chaotic regime. The route to chaos is written into the architecture of feedback. It is waiting inside every stable system you have ever encountered. And here is the institutional response. Feigenbaum submitted his first paper on this result to the journal Advances in Mathematics in November of 1976. It was rejected. He rewrote it and submitted to the Siam Journal of Applied Mathematics in April of 1977. It was rejected in October of 1977. The paper that contained one of the most significant discoveries in 20th century physics bounced between two journals for 2 years because the reviewers could not understand it, or did not believe it, or could not place it within any existing subdiscipline. It was too mathematical for the physicists and too physical for the mathematicians. It sat in Feigenbaum's desk drawer, along with the rejection letters, which he kept for years. The paper was finally published in 1978 in the Journal of Statistical Physics, Volume 19, pages 25 through 52. The title was Quantitative Universality for a Class of Nonlinear Transformations. It was published because the editor, Joel Lebowitz, decided to accept it on the basis of personal acquaintance with Feigenbaum, admitting that he did not fully understand the mathematics, but trusted the person behind it. Stephen Wolfram, in his obituary for Feigenbaum, who died on June 30th, 2019 at the age of 74, wrote that anything genuinely new or original, one could pretty much count on getting rejected by the peer review process, either through intellectual short-sightedness or through academic corruption. The experimental confirmation came in 1979 and 1980 from Albert Lidschaber's Rayleigh-Benard convection experiment at the École Normale Supérieure in Paris. Lidschaber heated a tiny cell of liquid mercury from below and measured the temperature oscillations at a single point as he slowly increased the temperature gradient. He observed period 2, period 4, period 8 oscillations, each bifurcation occurring at the interval predicted by Feigenbaum's constant, and then chaos. The theory was verified. The universal road to chaos was real. Feigenbaum and Lidschaber shared the 1986 Wolf Prize in Physics for this work. But the broader implication, the one that connects Feigenbaum to Lorenz and Poincaré and to the grid that ate itself in 2003, is still not part of how the world thinks about stability. The implication is that you do not need to understand the specific physics of a particular system to know that it can transition from stable to chaotic. You only need to know that it has nonlinear feedback and a parameter that can be pushed. That is all. If those two conditions are met, the Feigenbaum cascade is there, waiting. The road to chaos is already paved. The system just has not been driven far enough down it yet. And the systems we depend on most, the ones we assume are permanent, the power grids and financial markets and climate systems, and even the orbits of the planets, are all nonlinear. They all contain feedback, and they all have parameters that can be pushed. The question is not whether they contain the mechanism of their own instability. They do. The mathematics guarantees it. The question is whether the parameter is currently near the bifurcation point or far from it. And for several of the most important systems on Earth, the answer that has emerged from the data over the last 20 years is closer than anyone expected. I want to pause here and make sure something is clear, because it is the hinge on which everything that follows turns. The combination of Lorenz and Feigenbaum is not just a pair of related discoveries. Together, they constitute a complete theorem about the nature of stability. Lorenz proved that deterministic systems with nonlinear feedback can can be unpredictable. Feigenbaum proved that the route from stability to unpredictability is universal. Put those together and you get something that should have reshaped every field of engineering, every economic model, every risk assessment, every infrastructure plan on Earth. You get the statement that every nonlinear feedback system in the universe is sitting somewhere on the same road. The only thing that varies is how far down the road it has traveled. And here is the practical consequence that almost nobody talks about. If the route to chaos is universal, then the precursors to chaos are also universal. The period doubling cascade, the shortening intervals between bifurcations, the characteristic ratio of 4.6692, these are not just mathematical curiosities, they are early warning signs. If you have a system that is oscillating between two states, and you push a parameter and it starts oscillating between four states, you are on the Feigenbaum cascade. The next bifurcation will come faster, and the one after that faster still. And then chaos. You can calculate exactly how much room you have left before the transition, because the ratios are universal. The mathematics gives you a countdown timer, and almost nobody is using it. Climate scientists have begun to apply early warning indicators derived from bifurcation theory to tipping elements in the Earth system. The work by Van Westen and colleagues on the AMOC, which I will get to shortly, uses exactly this framework. But in finance, in infrastructure planning, in power grid management, the Feigenbaum framework is virtually absent. The tools exist, the mathematics is proved. The early warning signs are calculable, and the institutions that could use them are still running on Gaussian models and linear extrapolation. Lorenz proved that linear extrapolation fails for nonlinear systems. Feigenbaum proved that the failure follows a universal pattern, and the response has been to acknowledge the theory and ignore the practice. Because using the theory would mean accepting that the systems we depend on are not as stable as we need them to be. And that acceptance would cost money, careers, and the comfortable fiction that prediction works. There is a word for a system where the institutional incentives prevent the institution from absorbing the information it needs to survive. Feigenbaum would have recognized it. Lorenz would have smiled at it. The word is feedback. The same mathematics that describes the self-destruction of bridges and reactors also describes the self-destruction of institutions that refuse to learn from the mathematics of self-destruction. The loop is the same. The road is the same. And the ratio, 4.6692, does not care whether the system is made of steel, silicon, or human beings. That brings us to the physical world, to bridges and reactors, and the things we build with our hands that we believe will stand, and why they do not. On July 1st, 1940, a suspension bridge opened across the Tacoma Narrows in Washington state. It was the third longest suspension bridge in the world at the time, with a main span of 2,800 feet. It was elegant, it was slender, and from the very first day, it moved. In light winds, the bridge deck would undulate in gentle vertical waves, rising and falling as much as 5 feet at midspan. Drivers crossing the bridge reported the surreal experience of watching the car in front of them disappear into a dip and then rise back into view. Workers at the construction yard had already nicknamed it Galloping Gertie. The engineers were not especially worried. The deck was flexible and some movement was expected. They assumed the oscillations were a nuisance, not a danger. They tried various fixes. They attached cables from the deck to anchor points on the shore. They installed hydraulic buffers. Nothing worked particularly well, but the bridge continued to stand and carry traffic through the summer and into the fall. On November 7th, 1940, the wind was blowing at 40 to 42 miles per hour. Not a hurricane, not even a particularly strong storm, just a sustained, moderate wind. And at approximately 10 in the morning, something changed. The vertical oscillation, which had been the bridge's defining character for 4 months, suddenly transformed into a torsional oscillation. The deck began twisting along its length, one edge rising while the other fell, then reversing. The amplitude grew. Within minutes, the deck was rotating up to 45 degrees from horizontal. A reporter named Barney Elliott, who had come to film the bridge's motions, captured on 16mm film what happened next. The suspender cable bands which connected the deck to the main cables began to slip. The deck itself started to break apart. At 11:10 in the morning, a 600-foot section of the center span tore free and dropped into the narrows below. Here is what is important about the Tacoma Narrows collapse, and it is not the story you were told in physics class. For decades, physics textbooks used this bridge as an example of forced resonance. The wind was blowing at a frequency that happened to match the natural frequency of the bridge, and the bridge absorbed energy at that resonant frequency until it shook itself apart. That explanation is wrong. It has been wrong since it was first printed, and it is still being taught in some textbooks today. What actually destroyed the Tacoma Narrows Bridge was not resonance. It was a self-excited oscillation driven by aeroelastic flutter. The distinction matters enormously. In resonance, an external force drives a system at the system's natural frequency. In aeroelastic flutter, the system generates its own forcing through a feedback loop between its motion and the fluid flow around it. The bridge deck's shape, which was an H-section with solid plate girders, rather than the open truss design used by most suspension bridges, created a particular kind of interaction with the wind. When the deck twisted, the wind flowing over and under the deck generated vortices whose pattern depended on the angle of twist. Those vortices created forces that pushed the twist further, which changed the vortices, which increased the forces. The bridge was not being shaken by the wind, it was shaking itself. The wind was just the energy source, the feedback loop between the deck's motion and the aerodynamic forces was the mechanism, and the feedback was positive. Each cycle of oscillation pumped more energy in than the structural damping could absorb. The system was exhibiting negative aerodynamic damping, meaning the interaction with the airflow was adding energy to the oscillation rather than removing it. A panel convened by the Federal Works Agency after the collapse, including the legendary aerodynamicist Theodore von Karman, ruled that aerodynamic instability was the cause, not material failure, not manufacturing defect, not an unusually strong wind. The bridge destroyed itself because its own shape created a hidden feedback loop that the designers had not anticipated and could not see until the conditions were right for it to emerge. The conditions were not extreme. They were ordinary. 40 miles per hour is not unusual for the Tacoma Narrows. The bridge had simply encountered the parameter regime, where its hidden feedback loop transitioned from latent to active. That is the Feigenbaum pattern wearing a civil engineering costume, a system that appears stable, a parameter that shifts into a new range, a feedback loop that was always there, invisible, waiting, and then a transition so fast that nobody can intervene. Now hold that thought and jump forward 60 years to London. On June 10, 2000, the Millennium Bridge opened across the Thames between Tate Modern and St. Paul's Cathedral. It was a 333-metre footbridge, a shallow suspension design by architect Norman Foster and sculptor Anthony Caro, the first new crossing of the Thames in central London in over a century. It was beautiful. 80 to 90,000 people walked across it on opening day, with as many as 2,000 on the deck at any one time. Within minutes, the bridge started swaying, not up and down, like galloping Gertie, but side to side. Lateral oscillations at frequencies of about half a hertz, 0.8 hertz and 1 hertz. The amplitude grew until the measured accelerations reached nearly 2.5 meters per second squared. Pedestrians grabbed the railings. Some dropped to their knees. The footage, which you can still find, shows the entire bridge swaying rhythmically, while hundreds of people on it walk in a peculiar synchronized shuffle, everyone seeming to step at the same time. The bridge was closed on June 12th, 2 days after opening. It would not reopen until February of 2002, after engineers had installed 37 viscous fluid dampers at a cost of approximately £5 million. The explanation that entered the popular imagination, and the one that Stephen Strogatz and colleagues published in Nature in 2005, was beautiful and compelling. Pedestrians naturally walk at about 2 hertz, which means their lateral foot placement pushes sideways at about 1 hertz. If enough pedestrians are on the bridge, even a tiny lateral sway causes them to unconsciously adjust their gait to stay balanced, and that adjustment tends to synchronize with the sway, adding energy. More sway, more synchronization, more energy. A positive feedback loop between the crowd and the structure, mediated by the human balance reflex. Strogatz modeled this using the Kuramoto equations, the same mathematics that describes the synchronization of fireflies and pacemaker cells. It was a great story, except that in December of 2021, a team led by Igor Belich published a paper in Nature Communications that turned the explanation on its head. Their analysis, which examined data from more than 30 bridges worldwide, showed that the synchronization of pedestrian footsteps is not the cause of the lateral instability. It is the consequence. The actual mechanism is simpler, and, if you have been following the thread of this script, grimly familiar. Individual pedestrians walking out of sync with one another, each provide a small net lateral force when they step to maintain their balance on a moving surface. That force, averaged over a crowd, acts as negative damping. The crowd does not need to synchronize. Each person's independent attempt to not fall over adds a tiny amount of energy to the bridge's lateral oscillation. If the crowd is dense enough, the total energy input from this incoherent negative damping exceeds the bridge's structural damping. At that point, the oscillation grows. And once the oscillation is large enough, then pedestrians start synchronizing, because it is easier to walk in rhythm with a swaying bridge than against it. The synchronization is an effect, not a cause. Belich's team credited the original Arab engineers who had, back in 2000, suspected something like this before Strogatz's paper redirected the narrative. The engineers were right. The mechanism is a feedback loop between pedestrian balance correction and bridge motion, and it does not require the elegant synchronization story to work. It works with a disorganized, unsynchronized crowd. All you need is enough people. 2 bridges, 60 years apart, different materials, different designs, different engineers, different failure modes, different countries, and the same underlying mechanism. A hidden coupling between the structure's output, its motion, and its input, the forces acting on it. A positive feedback loop that is latent at low parameter values. The wind speed in one case, the crowd density in the other, and becomes active when the parameter crosses a threshold. The system did not fail because it was poorly designed. It failed because the feedback loop was invisible until the conditions revealed it. And the conditions were not extreme. They were ordinary. 40 miles per hour of wind. 2,000 people on a bridge. And if you are beginning to sense a pattern here, if you are beginning to suspect that this mechanism is not confined to bridges and weather models, and orbital mechanics, that it might be waiting inside every complex system humans have ever built. You are asking the right question, and the answer is worse than the question suggests, because the next example is not a bridge. It is a nuclear reactor, and the feedback loop inside it was not discovered after the failure. It was known beforehand. It was designed in, and when it activated, it killed people. On April 26, 1986, at 1:23 in the morning, the operators of Reactor 4 at the Chernobyl nuclear power plant near Pripyat, Ukraine, were conducting a safety test. The test was supposed to determine how long the turbines would spin and provide electricity after a loss of main electrical power, bridging the gap until emergency diesel generators came online. The test required the reactor to be running at low power, and it was running at low power, far too low. The operators had been trying to bring the reactor down to a target of 700 megawatts thermal for the test, but they overshot. Xenon poisoning, a buildup of the neutron-absorbing isotope xenon-135 that occurs when a reactor is held at reduced power, was strangling the chain reaction. The power dropped to approximately 30 megawatts, barely above shutdown. To recover, the operators made a decision that would kill them. They withdrew nearly all 211 control rods from the core, leaving an operational reactivity margin of about 6 to 8 rod equivalents. The regulation required a minimum of 30. At 1:23:04, the turbine test began. The reduced coolant flow caused the water in the pressure tubes to begin boiling. And here is where the hidden feedback loop of the RBMK reactor design became a death sentence. The RBMK reactor had what is called a positive void coefficient. In most pressurized water reactors used in the West, when coolant water boils and turns to steam, the void, the bubble of steam, absorbs fewer neutrons but also moderates them less. And the net effect is to reduce the chain reaction. Negative feedback. The reactor calms itself down, but in the RBMK design, the graphite moderator slowed the neutrons independently of the water, and the water primarily served as a neutron absorber. When the water boiled, it absorbed fewer neutrons, but the graphite was still moderating them just fine. More neutrons reached the uranium fuel. The chain reaction accelerated. More heat, more boiling, more voids, fewer absorbed neutrons, more chain reaction, positive feedback. And at low power, where the reactor was already starved of the dampening effects of a healthy neutron flux, the positive void coefficient was measured at plus 4.7 beta. That is a number that meant the reactor was, under those specific conditions, a bomb waiting for a trigger. At 1:23:40, operator Leonid Topchinov pressed the AZ5 button, the emergency shutdown. All 211 control rods were ordered to insert into the core simultaneously. And here the design delivered its final betrayal. The control rods of the RBMK were tipped with graphite displacers, intended to smooth the transition between rodded and unrodded states during normal operation. When the rods were fully withdrawn and then commanded to insert, the graphite tips entered the bottom of the core first, before the neutron-absorbing boron carbide section above them could reach the active zone. Graphite is a moderator. It increases reactivity, so the emergency shutdown, the button you press when everything is going wrong, momentarily made things worse. The bottom of the core got a burst of positive reactivity at exactly the moment the positive void coefficient was already driving the power upward. The reactor passed 530 megawatts within approximately 3 seconds. It kept going. Estimates of peak power range from 140 to 400 times the reactor's rated full thermal power. The fuel rods shattered. The pressure tubes burst. Approximately 30% of the fuel was blown through the bottom of the core into the space below. 2 explosions separated by 6 to 7 seconds, blew the 1,000-ton biological shield, the upper structure called Elena, off the top of the reactor building. The graphite caught fire and burned for more than 10 days, sending a plume of radioactive material across Europe. 31 people died in the immediate aftermath, most of them firefighters and plant workers, who absorbed lethal doses of radiation in the first hours. The total long-term death toll remains disputed, with estimates ranging from 4,000 to tens of thousands, depending on the methodology and the radius of study. The feedback loop that killed them was not hidden in the same way that the Tacoma Narrows loop was hidden. Engineers knew about the positive void coefficient. They knew about the graphite-tipped rods. They knew about the operational parameters that made low-power operation dangerous. What was hidden was the interaction between all of these factors simultaneously. The way the positive void coefficient at low power, combined with the positive scram effect of the graphite tips, combined with the near-total removal of control rods, combined with the xenon poisoning that had driven the operators to those extremes in the first place. Each individual factor was documented. The compound feedback, the cascade of positive reinforcements, was not. And that is the pattern. Not that the individual components of a system are unknown, but that the feedback between them creates a compound behavior that nobody anticipated. The bridge engineers knew about wind loads. They did not anticipate aeroelastic flutter from the specific deck geometry. The pedestrian bridge designers knew about lateral oscillation modes. They did not anticipate that a disorganized crowd could provide coherent negative damping. The reactor designers knew about positive void coefficients. They did not anticipate the compounding chain of positive feedbacks that the specific test conditions would activate. Each of these catastrophes was caused by the same mathematical structure, a hidden coupling between a system state and the forces that act on it, a feedback loop that amplifies deviations instead of damping them, a parameter, wind speed or crowd density or reactor power level that pushes the system across a bifurcation threshold, and a transition from stability to catastrophe on a timescale too fast for intervention. But those are physical systems, steel and concrete and uranium. You can argue that physical engineering is hard, that the materials and the forces are complex, and that these failures are tragic but specific to their domains. The implication that makes this universal, the one that connects Lorenz and Feigenbaum and Poincaré to the system you are embedded in right now, is that the same mathematics applies to systems that have no physical substance at all, to money, to information, to the abstract architectures of finance and infrastructure that modern civilization runs on. And in those systems, the feedback loops are not just hidden, they are deliberately designed in. In 1994, a man named John Meriwether founded a hedge fund called Long-Term Capital Management. Meriwether was not just any fund manager. He had been the head of the bond arbitrage group at Salomon Brothers, where he had built one of the most profitable trading desks on Wall Street before resigning in the wake of a 1991 Treasury auction scandal. His new fund attracted some of the most respected names in finance. The board included Myron Scholes and Robert Merton, who had won the Nobel Prize in Economics in 1997 for their work on options pricing theory. The Black-Scholes model, the mathematical framework they had helped develop, was the foundation of modern derivatives pricing. It was the equation that made Wall Street believe it had tamed risk. LTCM's strategy was convergence arbitrage. The fund identified pairs of securities whose prices had temporarily diverged from their historical relationship, usually government bonds from different countries or different maturities, and bet that the prices would converge back to normal. These were small mispricings, often fractions of a percent, but LTCM amplified them with massive leverage. For every dollar of actual capital, the fund borrowed 25 sometimes more. By early 1998, LTCM had approximately $5 billion in equity, $125 billion in assets on its balance sheet, and over $1,250 billion in off-balance sheet derivatives exposure. The fund had averaged about 40% annual returns since its founding. The models said the risk was manageable. The Nobel laureates had done the math. On August 17, 1998, Russia defaulted on its government bonds and devalued the ruble. The immediate financial damage was modest. Russia was not a major market, but the shockwave was not about Russia. It was about what Russia's default did to every other convergence trade in the world. Investors who had been calmly holding positions similar to LTCM's suddenly wanted out. Bond spreads that LTCM had bet would narrow, instead widened, and widened, and widened further. Here is the feedback loop. LTCM suffered losses on its positions. Those losses reduced its equity, which pushed its leverage ratio higher, from 25 to 1 toward 50 to 1 and beyond. The banks that had lent LTCM money, who had accepted its portfolio as collateral, looked at the deteriorating collateral value and issued margin calls. Meet the margin, or we will seize your assets. To meet the margin calls, LTCM had to sell positions, but selling into a panicking market pushed prices further against them, which generated more losses, which triggered more margin calls, which forced more selling. Loss, margin call, forced sale, bigger loss, bigger margin call, bigger forced sale. A positive feedback loop between the fund's balance sheet and the markets it was trading in. By the third week of September 1998, LTCM's leverage had climbed to approximately 130 to 1. The fund had lost $4.6 billion in 4 months. And because LTCM's positions were so large, its forced selling was itself moving the markets, which was destroying other funds that held similar positions, which was amplifying the selling pressure, which was destroying LTCM faster. The fund was not just a victim of the feedback loop, it was generating the feedback loop. Its own death throes were the mechanism of its death. On September 23, 1998, the president of the Federal Reserve Bank of New York, William McDonough, brokered an emergency meeting at the Fed's offices at 33 Liberty Street. 14 banks agreed to inject $3.625 billion into LTCM in exchange for 90% of the fund's equity. It was not technically a bailout using public money, but it was orchestrated by the Federal Reserve because the Fed believed that LTCM's uncontrolled collapse could take the global financial system with it. The derivatives exposure alone, more than $1 trillion notional, was entangled with every major bank on the planet. If LTCM's positions were liquidated in a fire sale, the cascading losses could have made 1998 look like 2008 arrived a decade early. The fund was dissolved in early 2000. Merriweather started another fund. The Nobel laureates went back to academia, and the financial system went right back to building the same kind of leveraged, interconnected, feedback-prone architecture that had nearly destroyed it. Because the lesson of LTCM was not that the mathematics of risk is wrong. The mathematics of risk is correct. The lesson is that the mathematics of risk explicitly tells you that feedback loops in leveraged systems produce fat-tailed distributions, extreme events that occur far more often than a normal distribution would predict. And the people who build these systems choose to use the normal distribution anyway, because the fat-tailed version is too frightening to model. They know the feedback loop is there. They choose not to look at it. 10 years after LTCM in 2008, the global financial system did exactly what the Fed had feared LTCM's collapse might trigger. The feedback architecture was the same. Mortgage-backed securities built on the assumption that housing prices would not decline nationwide simultaneously, were leveraged and cross-collateralized across every major bank. When housing prices did decline, the securities lost value. Banks holding them as collateral faced margin calls. They sold into a falling market. Prices dropped further. More margin calls, more selling, the same loss, call, sell, loss loop that destroyed LTCM, amplified to the scale of the entire global banking system. Lehman Brothers collapsed on September 15, 2008. The resulting cascade nearly brought down the world economy. The total damage, depending on how you measure it, was somewhere between $2 trillion and $22 trillion. And the fundamental mechanism, the hidden positive feedback loop between leverage and asset prices, was identical to the one that had been identified in the LTCM post-mortem a decade earlier. Identified, documented, published, and ignored. That same feedback architecture, 12 years later, ate the stock market in 36 minutes. On May 6, 2010, at approximately 2:32 in the afternoon Eastern Time, the Dow Jones Industrial Average began to fall. It fell fast. Within minutes, it had dropped 600 points. The decline accelerated. At its nadir, approximately 20 minutes after the plunge began, the Dow was down 998.5 points, roughly 9%, in what became the fastest intraday crash in the history of the stock market. Accenture, a company worth tens of billions of dollars, briefly traded at 1 cent per share. Apple, the most valuable company on earth, dropped approximately 35% before recovering. Procter & Gamble fell nearly 40% in minutes and then snapped back. Nearly $1 trillion in market capitalization vaporized and then reappeared, all within about 36 minutes. The trigger was a trade by a mutual fund company called Waddell & Reed, based in Kansas City. They had decided to sell 75,000 E-mini S and P500 futures contracts, a position worth approximately $4.1 billion, using an algorithmic execution system provided by Barclays. The algorithm was designed to sell at a rate calibrated to the current trading volume. As volume increased, the algorithm sold faster. As volume decreased, it sold slower. The idea was to minimize market impact by spreading the sales out over the normal flow of trading. But the algorithm had a design feature that turned it into a feedback mechanism. It used volume as its throttle, but it did not use price. It did not care whether the market was going up or down. It only cared how much trading was happening. And what happens when you start selling a large position into a market? Volume goes up. Other participants react. High-frequency trading firms, which made markets by rapidly buying and selling, absorbed some of the initial selling pressure, but their inventories filled up within seconds. So they started selling too, to other high-frequency firms, who absorbed and then dumped, who absorbed and then dumped. The SEC and CFTC joint report, published in September of 2010, described this as a hot potato effect. At one point, 27,000 E-mini contracts changed hands among high-frequency traders in 14 seconds. Nobody was holding inventory. Everyone was passing the position as fast as possible. And here is the loop. Volume went up because everyone was trading. The algorithm saw rising volume and sold faster. Faster selling caused more volume. More volume caused faster selling. The high-frequency traders, who normally provide liquidity by standing ready to buy and sell, pulled back because their risk models told them the market was behaving abnormally. Liquidity, prices, fell into a vacuum. And in that vacuum, quotes that had been set as placeholders, penny quotes and absurdly low bids that no one ever expected to be filled, suddenly became the best available price. That is why Accenture traded at a penny. Someone's algorithm sold into a market with no buyers except a standing bid at 1 cent. The market recovered because the Chicago Mercantile Exchange triggered an automatic 5-second trading halt on the E-mini when prices fell more than 5%. That pause broke the feedback loop. Humans and slower algorithms reassessed. Buyers re-entered. Prices snapped back. But the damage to the market's credibility was permanent. Circuit breakers were instituted afterwards. The SEC spent years studying the event. In 2015, the Department of Justice added a twist by charging a trader named Navinder Singh Sarao, operating from his parents' house in Hounslow, West London, with spoofing, placing and then cancelling large orders to manipulate the appearance of supply and demand. Sarao's spoofing did not cause the crash, but it may have added fuel to the feedback loop at a critical moment. His case illustrated how a single person operating from a bedroom could interact with a feedback-vulnerable system and amplify a cascade. The 2003 blackout, the 1998 LTCM collapse, and the 2010 flash crash are 3 events in 3 different domains: electrical engineering, finance, and automated trading that share the same mathematical skeleton. A system operating near normal conditions, a perturbation that should have been absorbed by the system's built-in resilience, a hidden feedback loop that amplifies the perturbation instead of damping it, and a cascade so fast that human intervention is impossible. I want to make something explicit that has been building through these examples because the pattern deserves to be named. In every one of these cases, the hidden feedback loop was not hidden because it was unknown. The aerodynamics of bluff bodies in crossflow had been studied since the 19th century. The positive void coefficient of the RBMK was documented in the design specifications. The lateral oscillation modes of footbridges were known to civil engineers. The feedback was hidden because it was dismissed, because the engineers and operators believed that the safety margins and protective systems they had designed into the structure would contain the feedback before it could grow. They believed in their own buffers. They believed in their redundancies. They believed in the gap between normal operating conditions and the parameter regime where the feedback would activate. And that belief, in every case, was based on a linear model of the safety margin, a model that assumed perturbations would grow proportionally to their size, a model that assumed you could extrapolate from the behavior of the system at normal parameters to predict its behavior at extreme parameters, a model that Lorenz had proved was wrong for any nonlinear system in 1963, and that Feigenbaum had proved was universally wrong in 1978. The engineers were not incompetent. They were using the best tools their training provided. But their training was Newtonian, their tools were linear, and the systems they were building were neither. There is a phrase that shows up in accident investigation reports across every domain. It was not foreseen. The compound interaction of factors was not foreseen. That phrase is the institutional version of Lorenz's discovery. It is the admission that the system's behavior at the failure point could not have been predicted from its behavior under normal conditions, because the feedback structure that caused the failure was nonlinear and therefore invisible to linear extrapolation. And it will keep showing up in accident reports for as long as institutions continue to design safety margins using linear tools for nonlinear systems, which, as of today, is essentially all of them. Lorenz's discovery was not about weather. It was about the mathematical structure of feedback in nonlinear systems. Weather was just the system he happened to be studying when the rounding error revealed the truth. The truth applies equally to the atmosphere, the power grid, and the core of a nuclear reactor. It applies to anything with a loop. And in each case, after the catastrophe, the same institutional response. investigations, reports, new regulations, new circuit breakers, new stress tests, and then, within a few years, the same architecture rebuilt with the same vulnerabilities. Because the fundamental lesson that nonlinear feedback in coupled systems produces catastrophic transitions that cannot be predicted from the behavior of individual components is a lesson that institutional decision-making is constitutionally incapable of absorbing, not because the people are stupid, but because the premise of institutional planning is prediction. And the mathematics of feedback says prediction is bounded. Accepting that would mean accepting that the systems we depend on cannot be made safe. They can only be made resilient. And resilience is expensive, unglamorous, and does not fit in a quarterly earnings report. This should disturb you, but it is still not the worst part, because everything I have described so far, the bridges and reactors and markets and grids, are systems built by humans, systems we designed, systems we could, in principle, redesign. The worst part is that the same feedback structure exists in systems we did not build, cannot redesign, and are currently pushing toward their bifurcation points with no plan for what happens when they cross. The Arctic Ocean is a feedback loop in disguise. When it is covered in ice, as it has been for most of human history, the ice reflects between 50 and 70% of the incoming solar radiation back into space. White surfaces bounce sunlight. The energy never enters the ocean. It never becomes heat. The ice preserves itself by keeping its own environment cold. When the ice melts, the dark water underneath absorbs roughly 94% of the incoming solar radiation. The ocean warms. The warmer ocean melts more ice. Less ice means more dark water. More dark water means more absorption. More absorption means more warming. More warming means more melting. This is the ice albedo feedback, and it is one of the cleanest examples of a positive feedback loop in the Earth system. It has been known since at least the 1950s. It is in every climate science textbook, and a 2014 paper by Christina Pistone, Ian Eisenman, and V. Ramanathan in the Proceedings of the National Academy of Sciences measured the actual radiative forcing from Arctic sea ice loss between 1979 and 2011. The number was 6.4 watts per square meter over the Arctic Ocean, plus or minus 0.9. Averaged over the entire globe, that is approximately 0.21 watts per square meter. To put that in context, the total additional radiative forcing from the increase in atmospheric carbon dioxide over the same period was about 1.7 watts per square meter. The ice albedo feedback from just the Arctic was adding the equivalent of more than 12% of the total CO2 forcing, not from any new emissions, but from the ice that was already gone. That is not a future projection. That is a measurement. It has already happened. And the more ice that disappears, the stronger the loop gets. Each percentage point of ice lost increases the rate at which the next percentage point melts. The system is accelerating along the upward slope of a positive feedback curve. But the ice albedo loop is not alone. It is one of at least a dozen positive feedbacks in the Earth's climate system. And the most dangerous ones are the ones that can trigger each other. Underneath the permafrost in Siberia, northern Canada, and Alaska sits a reservoir of organic carbon that was frozen into the soil during the last ice age. It has been sitting there for tens of thousands of years, locked in place by temperatures that kept the ground permanently frozen. The total amount of carbon in northern permafrost soils, as estimated by a synthesis of studies summarized by NOAA's Arctic Report Card in 2019, is between 1,460 and 1,600 billion metric tons. For reference, the total amount of carbon currently in the atmosphere is approximately 870 billion metric tons. The permafrost holds roughly twice as much carbon as the entire atmosphere. As the Arctic warms, and it is warming 2 to 3 times faster than the global average, the permafrost thaws. Microorganisms that have been dormant for millennia wake up and begin to decompose the organic matter. Some of that decomposition produces carbon dioxide. Some of it, particularly in waterlogged, oxygen-poor conditions like thermokarst lakes, produces methane. Methane's global warming potential is roughly 30 times that of CO2 over a 100-year timescale and about 80 times over a 20-year timescale. A paper by Turetsky and colleagues, published in Nature Geoscience in 2019, estimated that abrupt thermokarst thaw could add approximately 40% to the total permafrost carbon release, a contribution not captured by models that assume gradual top-down thawing. Here is the feedback. Warming thaws permafrost. Thawing permafrost releases carbon. Released carbon causes more warming. More warming thaws more permafrost. This is the permafrost carbon feedback, and its terrifying property is that it operates on a timescale of decades to centuries, long after the initial warming trigger might be controlled. Even if humanity stopped all emissions tomorrow, the permafrost that has already begun to thaw will continue to release carbon for centuries. Some of the organic material in the permafrost is 50,000 years old. Mammoths walked on it. The carbon it contains was locked away before the last ice age ended, before agriculture, before writing, before cities. And now it is thawing, because the Arctic is warming at 2 to 3 times the global average, and the microorganisms that will decompose it do not know or care how long it has been frozen. The feedback loop is already running. The only question is how fast. And then there is the Atlantic Meridional Overturning Circulation, the AMOC, the system of ocean currents that carries warm water from the tropics northward along the surface of the Atlantic, where it cools, becomes denser, sinks, and returns south along the ocean floor. The AMOC is what keeps Europe roughly 5 to 10 degrees Celsius warmer than it should be for its latitude. London is at the same latitude as Calgary. Oslo is at the same latitude as Anchorage. The reason those cities have moderate climates is the AMOC. In February of 2021, Stefan Rahmstorff and colleagues published a paper in Nature Geoscience showing that the AMOC is currently at its weakest in over 1,000 years. Their proxy reconstructions, based on sea surface temperature patterns and sediment cores, indicate a decline of approximately 15% since the mid-20th century. The mechanism is freshwater influx from Greenland ice melt and increased Arctic runoff, which dilutes the surface salinity in the North Atlantic, reducing the density of the water, making it less likely to sink and slowing the circulation. And here is the feedback. A slower AMOC transports less heat northward, which changes atmospheric patterns, which can alter precipitation over the North Atlantic, which can add more fresh water, which slows the AMOC further. In 2023, René van Westen, Michael Cliffhouse, and Henk Dijkstra published a paper with models run in CES-M1 showing that the AMOC has an internal feedback structure consistent with a tipping element. Their early warning indicators suggested that the circulation could reach a bifurcation point, a critical threshold beyond which it would collapse to a fundamentally different state within decades to a century. The collapse would not be gradual. It would be a regime change. The AMOC would shift from its current strong state to a weak or off state on a timescale of years to decades, not centuries. And once collapsed, it would not easily restart. The system has hysteresis. You can push it over the edge, but you cannot easily push it back. I need to connect these back to the mathematics we have been building, because the point is not that climate change is dangerous. You already know that. The point is that climate systems are nonlinear feedback systems. They obey the same mathematics that Lorenz discovered in 1961, the same universality that Feigenbaum proved in 1978, the same cascade dynamics that destroyed the Tacoma Narrows and Chernobyl and the Northeast power grid. Climate tipping points are bifurcation points. They are the parameter values beyond which the hidden positive feedback loops in the Earth system transition from latent to active, exactly as the wind speed at Tacoma Narrows transitioned the bridge's latent aeroelastic flutter from invisible to catastrophic. A 2019 paper in Nature by Timothy Lenton, Johann Rockström, Hans-Joachim Schallnhuber, and colleagues identified over a dozen potential tipping elements in the Earth system, including Arctic sea ice, the Greenland ice sheet, the West Antarctic ice sheet, the Amazon rainforest, the AMOC, the permafrost, coral reef systems, and the Indian monsoon. They argued that several of these may be approaching their critical thresholds at current warming levels, and that the interaction between them, the coupling, could create a tipping cascade, a domino sequence in which the collapse of one element pushes another across its threshold. Think about what that means in the language of this script. Each tipping element is a system with a hidden positive feedback loop. Each one has a parameter, global temperature, that is being pushed. Each one has a bifurcation point beyond which it transitions irreversibly to a new state, and they are coupled to each other. The collapse of Arctic sea ice amplifies warming, which accelerates permafrost thaw, which releases more carbon, which pushes temperature higher, which threatens the AMOC, which changes precipitation patterns, which affects the Amazon, which changes carbon uptake, which raises temperature further. The engineering catastrophes I described earlier were isolated. The Tacoma Narrows Bridge collapsed, and no other bridge collapsed as a result. Chernobyl melted down, and no other reactor melted down as a result. Each failure was contained because the systems were not coupled. Climate tipping elements are coupled. A cascade in the climate system is not a metaphor. It is a description of a coupled, nonlinear dynamical system being pushed through a series of bifurcation points. And the mathematics of coupled, nonlinear systems with multiple feedback loops is exactly the mathematics that Poincaré found hiding in the three-body problem in 1889. The mathematics of chaos. The mathematics that says long-term prediction becomes impossible once the system crosses the Lyapunov threshold. We are conducting an experiment on the only planet we have, pushing parameters that control coupled nonlinear feedback loops in a system whose Lyapunov time may be decades, using models that we know from the mathematics Lorenz proved in 1963 have fundamental prediction limits. And the people running this experiment, the policymakers and economists and energy companies, are operating on the Newtonian premise, the premise that says, if we understand the components well enough, we can predict and control the outcome. The premise that was disproved in 1963 and has been failing spectacularly in every domain that involves nonlinear feedback ever since. The calculations have been done. The papers have been published. The feedback loops have been identified, measured, and modeled. And the institutional response has been precisely what it was after Lorenz published in 1963. After Feigenbaum was rejected twice, after LTCM collapsed, and the same architecture was rebuilt within a decade, the response has been to acknowledge the risk in technical reports and then to continue operating on the assumption that stability is the default. Because the alternative where stability is the exception and the mathematics guarantees eventual bifurcation, is an alternative that our institutions are not built to process. And still we have not reached the bottom. Because everything I have described so far, every example, every catastrophe, every hidden feedback loop has been about systems that exist within the universe. Systems embedded in physics, in chemistry, in economics, in engineering. The deepest implication of what Lorenz and Feigenbaum and Poincaré discovered is not about any individual system. It is about the architecture of the universe itself. I want to go back to Poincaré for a moment, because what he wrote in 1908 has never been fully reckoned with. In his book, Science et Méthode, in a chapter called Le Hasard, which means chance, he wrote a passage that is essentially the butterfly effect stated in formal French, 53 years before Lorenz touched a computer. The passage, in translation, reads like this: "It may happen that small differences in the initial conditions produce very great ones in the final phenomena. A small error in the former will produce an enormous error in the latter. Prediction becomes impossible, and we have the fortuitous phenomenon." And then, in the very next paragraph, he applied this principle to weather and to the formation of cyclones. Poincaré saw it. He stated it clearly. He published it in a widely read book, and the scientific community, for more than half a century, did nothing with it, not because it was obscure. Science et Méthode was translated into English, German, Spanish, and several other languages. It was read by physicists, mathematicians, philosophers. The passage about sensitive dependence and the impossibility of prediction was right there, in print, in plain language, and it was treated as a philosophical curiosity, an interesting observation about the limits of measurement, rather than what it actually was, a fundamental theorem about the structure of dynamical systems that will be independently rediscovered by Lorenz in 1961 and formally quantified by Feigenbaum in 1975. This pattern of discovery and suppression, or more precisely, discovery and neglect, is not incidental to the story of chaos theory. It is central, and it does not stop with Poincaré. Benoit Mandelbrot was born in Warsaw, Poland on November 20th, 1924, into a family that was already running from history. His family moved to France in 1936 to escape the rising threat in Eastern Europe. He survived the German occupation by living in provincial towns and working as an apprentice toolmaker. After the war, he attended the École Polytechnique in Paris, earned a master's at Caltech in aeronautical engineering, and then returned to France for his doctorate under the supervision of Paul Lévy. He was brilliant, visionary, and constitutionally incapable of staying within the boundaries of any single academic discipline. He studied the distribution of income, the geometry of coastlines, the noise in telephone transmission lines, the fluctuations of commodity prices, the branching of rivers, and the structure of turbulence. In every domain he entered, he found the same thing, the same rough, fragmented, self-similar geometry that did not fit the smooth curves of Euclidean mathematics and the Gaussian statistics that the establishment relied on. He called these objects fractals, a term he coined in 1975. His two books on the subject, Les Objets Fractals in 1975 and The Fractal Geometry of Nature in 1982, became iconic. The Mandelbrot set, the infinitely complex boundary of a simple iterative map in the complex plane, became one of the most recognized images in all of mathematics. But the mathematical establishment did not want him. He spent the bulk of his career at IBM's Thomas J. Watson Research Center in Yorktown Heights, New York, not at a university, at a corporate laboratory, because the mathematics departments at major universities were dominated by the Bourbaki school. a group of French mathematicians who valued abstraction, formalism, and axiomatic purity above all else. Mandelbrot's work was too concrete, too applied, too rooted in the messy geometry of the real world. He worked on economics and turbulence and signal processing and coastlines. That was not mathematics. That was dabbling. He did not receive a tenured position at a university until 1999, when Yale offered him a sterling professorship. He was 75 years old, the oldest person in Yale's history to receive tenure. Mandelbrot himself once wrote that he was determined to stay away from established mathematics so that he could feel the excitement of being the first to find a degree of order in some real, concrete, and complex area where everyone else saw a lawless mess. The pattern repeats itself. Poincaré's discovery, buried by indifference. Lorenz's paper, ignored for a decade because it was published in a weather journal. Feigenbaum's universality result, rejected twice. Mandelbrot exiled to a corporate lab because his geometry was too real for the formalists. In each case, the people who discovered fundamental truths about the architecture of instability and feedback were marginalized by the institutions that should have recognized and amplified their work. And in each case, the marginalization was not ideological or conspiratorial. It was structural. Institutional science, like any complex system, has its own feedback loops. Grant committees reward safe, incremental research. Peer review favors work that fits within established subdisciplines. Career advancement depends on publishing in the right journals, which means writing for reviewers who share your framework. A truly novel result, one that crosses boundaries and challenges premises, triggers the immune system of the institution. It is rejected not because it is wrong, but because it is inconvenient. And here is the irony that Mandelbrot would have appreciated. The institutional dynamics that suppressed chaos theory for decades are themselves a nonlinear feedback system with hidden positive loops. A paradigm suppresses dissent, which prevents paradigm change, which strengthens the paradigm, which increases the suppression of dissent. Thomas Kuhn described this in The Structure of Scientific Revolutions in 1962, 1 year before Lorenz published Deterministic Non-Periodic Flow. The resistance to chaos theory was itself a demonstration of the principles that chaos theory describes. The system was protecting its own stability, and eventually, when enough anomalous data accumulated, when enough independent researchers converged on the same conclusions, the paradigm shifted, not gradually, abruptly, a bifurcation, a regime change. The same mathematics all the way down. But I promised you the deepest implication, and we are not there yet, because everything I have told you so far is about systems within the universe. Weather systems, solar systems, bridges, reactors, markets, climate, scientific institutions. They are all embedded in the physical universe, governed by its laws, subject to its dynamics. The deepest question, the one that I do not think has been adequately confronted even within the chaos theory community, is whether the universe itself is a system with hidden feedback loops heading towards its own bifurcation point. The second law of thermodynamics states that the total entropy of an isolated system can only increase over time. This is often described as a tendency toward disorder, but that is not quite right. It is a tendency toward equilibrium, toward the state with the maximum number of accessible microstates, toward the configuration from which there is no thermodynamic force to drive further change. In an expanding universe, the relevant equilibrium is heat death, a state in which all matter is uniformly distributed. All temperature gradients have been smoothed out, and no further work can be extracted from any part of the system. The timescale for this is on the order of 10 to the 100th power years, which is so far beyond any human comprehension that it might seem irrelevant. But the mathematics of the second law has a structure that should look familiar by now. The second law is a feedback loop. The universe begins in a low entropy state, a state far from equilibrium, a state with enormous gradients and enormous potential for work. Stars form, chemistry happens, life emerges. All of this is driven by the flow of energy from concentrations toward dispersal, from order toward entropy. And every process that dissipates energy, every star that burns, every cell that metabolizes, every thought you think, increases the total entropy and moves the universe closer to equilibrium. The universe's own activity, the very thing that makes it interesting, is the mechanism by which it moves toward the state in which nothing interesting can happen anymore. Creation is the feedback loop that drives destruction, and it is positive. Every dissipative process makes the next dissipative process more likely, because the gradients that drive them are being consumed, and the universe is falling faster and faster into the basin of attraction that is maximum entropy. This is not metaphorical. This is thermodynamics. The arrow of time, the reason you remember yesterday but not tomorrow, the reason eggs break but never unbreak, the reason every organized system you have ever seen is temporary, is a consequence of the second law, and the second law is a consequence of the initial conditions of the universe. The Big Bang produced a state of extraordinarily low entropy, a state so far from equilibrium that the relaxation toward equilibrium has been ongoing for 13.8 billion years, and will continue for timescales that dwarf the current age of the universe by factors of 10 to the 90th. You are part of this process. Every neuron firing in your brain, every muscle contracting, every breath you take is a dissipative event that increases the total entropy of the universe. You are not fighting entropy. You are an instrument of it, a temporary eddy in the thermodynamic current, a dissipative structure in the language of Ilya Prigogine, which is to say, a structure that exists not in spite of entropy, but because of it. The same energy gradients that are driving the universe toward heat death are, temporarily and locally, organized into patterns of staggering complexity. You, your consciousness, your civilization, your planet, all of it powered by the flow from low entropy to high entropy. All of it temporary. All of it a feedback loop executing its own dissolution. And here is where Lorenz and Feigenbaum connect to cosmology. Because the question of whether the universe's descent toward equilibrium is smooth and predictable, a gradual, linear, manageable decline, or whether it contains within it the same kind of nonlinear feedback dynamics that produce sudden bifurcations, catastrophic transitions, and sensitive dependence on initial conditions, is not a settled question. The Lorenz attractor shows that a simple three-variable system with nonlinear feedback can produce unpredictable behavior forever. The universe has not three variables, but an effectively infinite number. Its dynamics are governed by equations, the Einstein field equations, the Standard Model, quantum field theory, that are profoundly nonlinear. The assumption that the universe's evolution will be smooth, that the cosmological future can be extrapolated from the cosmological present using linear models, is exactly the Newtonian premise that Lorenz disproved for weather, that Lasker disproved for the solar system, and that every catastrophe I have described in this script has disproved for human systems. Lee Smolin proposed in 1992 what he called cosmological natural selection. The hypothesis is that black hole singularities bounce into new universes whose physical constants vary slightly from the parent. Universes whose constants happen to produce more black holes, produce more offspring. And over many generations, the multiverse population is dominated by universes whose constants are tuned to maximize black hole production. It is a Darwinian feedback loop at the cosmological scale. The universe's own dynamics produce structures, black holes, that produce more universes, which produce more structures. It is a positive feedback loop applied to the generation of reality itself. Smolin made a specific, falsifiable prediction. If cosmological natural selection is correct, the physical constants should be optimized for black hole production, which means, among other things, that no neutron star should exist with a mass above about 1.6 solar masses, because beyond that mass, the star would collapse to a black hole, and the constants should be tuned to make that threshold as low as possible. In 2010, the Shapiro delay measurement of pulsar PSR J16 14-2230 yielded a neutron star mass of approximately 2 solar masses. A subsequent measurement of PSR J0740 + 6 gave approximately 2.08 solar masses. The specific prediction failed. Smolin has proposed modifications, but the strong form of the hypothesis is experimentally falsified. I tell you this not to dismiss cosmological natural selection, but to make a point about intellectual honesty. The hypothesis failed a specific test, and that failure should be stated clearly. But the broader framework, the idea that the universe might contain feedback loops operating at the cosmological scale that shape its own evolution, has not been falsified. It has barely been investigated. And the reason it has barely been investigated is the same institutional dynamic that delayed Lorenz and rejected Feigenbaum and exiled Mandelbrot. The question of whether the universe is a feedback system is too big, too cross-disciplinary, too resistant to the kind of narrow quantitative answer that earns publications and grants. So it sits, like Poincaré's memoir sat, like Lorenz's paper sat, like the Feigenbaum constants sat in a Los Alamos desk drawer, waiting for someone to ask the uncomfortable question and then refusing to look away from the answer. The question this script has been building toward is not whether individual systems contain hidden feedback loops. They do, that is proved. It is not whether those feedback loops can produce catastrophic transitions. They can. That is demonstrated. It is not whether the mathematics of universality guarantees that the road from stability to chaos is the same for all systems. It does. That is confirmed. The question is whether stability itself, at any scale, from a heartbeat to a bridge to a market to a climate to a planetary orbit to the vacuum state of the universe, is anything more than a transient phase in a dynamical system that has not yet been pushed to its bifurcation point. The mathematics says no. The data, from Poincaré through Lorenz, through Feigenbaum, through Lasker, says no. Every example in the historical record, from the solar system's 5 million year Lyapunov time to the 4-minute cascade that took out the Northeast grid, says no. Stability is not a property of systems. It is a phase. And phases end. I want to take you back to where we started, to the tree branch in Ohio, to the software bug, to the 4 minutes. The investigation after the 2003 blackout concluded that the cascade was unstoppable once it began. Once the first protective relay tripped, the redistribution of power loaded the next line beyond capacity faster than any human being could process the information. The grid's own protective mechanisms, the relays designed to isolate failures and prevent damage, became the propagation mechanism. Each relay that tripped to protect its own line pushed more power onto the neighboring lines, which tripped their own relays, which pushed more power onto the next set of lines. The system designed to prevent catastrophe was the system that caused the catastrophe to propagate. Protection and destruction were the same mechanism, the same feedback loop, the same mathematics. 508 generating units, 265 power plants, 55 million people, 11 deaths, $6 billion, 4 minutes. And the cause was not the tree branch. The cause was not the software bug. The cause was that the power grid, like every complex system, with nonlinear feedback, had been designed on the premise that stability is the default, that perturbations will be absorbed, that failures will be contained, that the system will return to equilibrium after a shock. And that premise, the Newtonian premise, the premise that carried Western civilization from Principia Mathematica through the Industrial Revolution, through the space age, is the premise that a meteorologist at MIT disproved in January of 1961 because he went to get a cup of coffee and typed 0.506 instead of 0.506, 1, 2, 7. That is not a failure of engineering. That is not a failure of regulation. That is not a failure of human vigilance. That is the mathematics of reality asserting itself through the structures we build without understanding what we are building on. We build on the assumption that stability is the ground state. The mathematics says stability is the excited state. And excited states decay, Poincaré knew. He wrote it down in 1890 and again in 1908, but the implication was too uncomfortable, and so the mathematical community filed it under pathologies and moved on. Lorenz knew. He published it in 1963, but it was in a weather journal, and the physicists and the mathematicians and the engineers did not read weather journals, and so the result sat for a decade. Feigenbaum knew. He proved it was universal in 1975, but the journals would not print it, and the proof sat in a desk drawer for 3 years. The pattern is always the same. The mathematics is discovered. The mathematics is correct. The mathematics is uncomfortable. And the institutions that most need to understand it are the institutions least capable of absorbing it, because their entire operating model is built on the premise that the mathematics disproves. Mandelbrot spent his career finding the fingerprints of chaos in the real world, in financial markets, in turbulence, in the geometry of nature. He found that the distributions of price changes in financial markets are not Gaussian, not bell-shaped, not well-behaved. They have fat tails. Extreme events occur far more often than the normal distribution predicts. This is exactly what you would expect from a nonlinear feedback system, and the financial industry's response was to continue using Gaussian models to continue pricing risk as if extreme events were negligible, and to be stunned when extreme events destroyed their portfolios. LTCM, 2008, the flash crash. Each time, the same surprise. Each time, the same mathematics that said the surprise was inevitable. Lorenz died in 2008. By then, his work had been recognized with nearly every major prize available to someone who works outside the Nobel categories. But the broader implication of what he found, the implication that extends beyond weather to every system with nonlinear feedback, was still being processed. It is still being processed now. The Kyoto Prize citation called chaos theory, one of the most dramatic changes in mankind's view of nature since Sir Isaac Newton. But Newton's view is still the operating system. Lorenz's correction has been acknowledged by the scientific community and ignored by every institution that plans, builds, regulates, or governs. You live inside that gap, the gap between what the mathematics says and what the institutions believe. You ride the subway across a bridge designed on Newtonian premises. You invest your savings in markets modeled with Gaussian distributions. You plan your life on a planet whose climate has positive feedback loops that the policymakers have identified but not integrated into their decision frameworks. You sit on a planet whose orbit is chaotic on a timescale of 5 million years, held in its current configuration by a relativistic correction that Newton could not have known about. In a solar system where the mathematics says 1% of futures end with Mercury colliding with the Sun, the Feigenbaum constants are universal. The road to chaos is the same for all systems, and the road is always there, underneath the surface of every stable state, waiting for the parameter to move. The bridge stood for 4 months before the feedback loop found its moment. The power grid ran for decades before the cascade found its 4 minutes. The solar system has been stable for 4.5 billion years, but the Lyapunov time is 5 million years, and the orbit has rolled the dice 900 times. And Lasker's simulations show that the next 5 billion years are not guaranteed. Lorenz went to get a cup of coffee. He came back to find that the universe does not keep its promises, that the future is not a continuation of the past, that the ground you are standing on is not ground at all. It is a system, and every system has a feedback loop it does not know about. And every feedback loop, given time, finds its way to the surface. He typed 3 decimal places instead of 6. The difference was less than 1 part in 5,000, and the weather of an entire simulated planet changed. Now think about the systems you depend on: the grid, the market, the climate, the orbit, the vacuum state of the field that gives particles their mass. Every one of them is a nonlinear dynamical system with feedback. Every one of them has a Lyapunov exponent. Every one of them has a bifurcation point somewhere in its parameter space. And for every one of them, the question is not whether the hidden feedback loop exists. The mathematics guarantees that it does. The question is how close the parameter is to the threshold. You do not know the answer. Neither do the people who built the system. Neither did the engineers who opened Galloping Gertie to traffic on a sunny day in July. Neither did the operators at Chernobyl at 1 in the morning. Neither did the quants at long-term capital management when they leveraged themselves 130 to 1. Neither did the algorithm at Waddell and Reed when it sold into rising volume. The feedback loop is always invisible right up until the moment it is the only thing that matters. Poincaré proved this in 1889 and tried to destroy the proof. Lorenz confirmed it in 1961, and nobody noticed. Feigenbaum generalized it in 1975, and nobody would publish it. Mandelbrot spent his career mapping it and was denied a permanent academic position until he was 75. Lorenz once said, in his typically understated way, that he was not sure whether the theoretical limit to weather prediction was about 2 weeks, or whether improved observations and models might push it to 3 or even 4 weeks. He was careful. He never claimed more than the mathematics supported, but the mathematics supported a revolution, and the revolution has still not fully arrived. The mathematics is there. It has always been there. It is precise, it is proved, and it is universal. It says that the thing you call stability is the thing that precedes collapse. Not always, not in every case, but with a probability that is non-zero, that cannot be reduced to 0, and that accumulates over time. The longer a system has been stable, the more parameters have had time to drift. The more feedback loops have had time to couple, the more the Lyapunov exponent has had time to do its work. And right now, on this planet, in this century, multiple coupled nonlinear systems are being pushed toward their bifurcation points simultaneously. The Arctic ice, the permafrost, the AMOC, the financial architecture, the power infrastructure, the geopolitical order. Each one is a system with hidden positive feedback loops, and they are not isolated from each other. They are coupled. What happens in the climate affects the economy. What happens in the economy affects the infrastructure. What happens in the infrastructure affects the society. The mathematics of coupled, non-linear systems with multiple feedback loops is the mathematics that Poincaré found hiding in 3 gravitating bodies in 1889. And Poincaré's conclusion was that prediction becomes impossible. There is a number that describes how fast errors grow in any chaotic system. It is called the Lyapunov exponent. Lorenz measured it for the atmosphere. Lasker measured it for the solar system. It can be estimated for financial markets, for power grids, for ecological systems. For each system, it gives you a time scale, the Lyapunov time, beyond which prediction is fundamentally meaningless. And for the coupled system of systems that constitutes human civilization sitting on top of a nonlinear planet, nobody has calculated that number. Nobody has even attempted to, because the calculation would require treating the entire interconnected web of climate, economy, infrastructure, and society as a single dynamical system and measuring its sensitivity to perturbation. And the answer, whatever it is, would be too uncomfortable to publish. Lorenz's 3 equations gave a Lyapunov time of roughly 1 in dimensionless units. 12 variables gave a prediction horizon of about 2 weeks for weather. The full coupled Earth system, with its ice and ocean and permafrost and circulation and ecosystems and human economies, has a number of effectively interacting variables that is beyond counting. The Lyapunov time for the system you are embedded in right now could be decades. It could be years. There is no way to know without doing the calculation that nobody is willing to do. And here is the final thing I want you to sit with. The mathematics of chaos does not say that catastrophe is certain. It says that stability is not guaranteed. It says that the systems we depend on are not in equilibrium. They are in a transient state that resembles equilibrium on timescales shorter than their Lyapunov time. And when the Lyapunov time is exceeded, the system enters a regime where its behavior becomes sensitive to perturbations so small that they cannot be measured, cannot be controlled, and cannot be predicted. A tree branch, a rounding error, a test at a nuclear plant, a trade in Kansas City, a degree of warming, a fraction of a % of ice gone. These are not the causes. They are the perturbations that reveal the feedback loop that was always there. The cause is the architecture. The cause is the feedback. And the feedback is universal. Lorenz went to get a cup of coffee and came back to a different world. He spent the rest of his life trying to tell people what he had found. He published it. He won prizes for it. He explained it as clearly as anyone could explain it. And the institutions that most needed to hear it continued to plan and build and govern as if stability were the ground state of the universe. It is not. It never was. And the mathematics that proves this has been sitting in the open, published, verified, and confirmed since 1963, since 1890, if you count Poincaré, since 1908, if you count the passage in Science et Méthode that spelled out the butterfly effect half a century before Lorenz. The feedback loops are real. They are in the bridges and the reactors, and the markets, and the grids, and the ice, and the ocean, and the soil, and the orbits, and the atoms. They are in the equations that govern the vacuum state of the Higgs field. They are in the thermodynamic arrow that drives every process in the universe toward maximum entropy. They are in you, in the dissipative biochemistry that sustains your thoughts, in the neural feedback that sustains your consciousness, in the cardiac rhythm that sustains your life, and every one of them is waiting for its parameter to move. Edward Lorenz was 90 years old when he died. He had hiked the White Mountains until roughly 2 weeks before the end. He had spent the last 4 decades of his life as the man who proved that the future is not a deterministic function of the present in any usable sense. He did not seek fame. He did not campaign for his ideas. He published his papers, gave his lectures, answered his mail, and went hiking. He was, by all accounts, a man of extraordinary calm for someone who had discovered that calm is an illusion. His 1972 talk, the one with the butterfly in the title that he did not choose, ended with a passage that I think deserves to be the last thing you hear in this script. After 2,000 words of careful, measured, technical argument about whether the atmosphere is unstable with respect to small perturbations, Lorenz arrived at his conclusion. He acknowledged that he had not proved instability. He acknowledged that the question remained formally open. And then he said that the evidence for instability is overwhelming, not suggestive, not compelling, overwhelming. He said this in 1972. The evidence has only grown since then. Lasker's solar system simulations, the 2003 blackout, the 2010 flash crash, the ice albedo measurements, the AMOC proxies, the permafrost carbon inventories. Every one of these is a data point in the case that Lorenz opened in 1963, the case that Poincaré opened in 1889, the case that says stability is the thing that exists between bifurcations, and bifurcations are the thing that the mathematics guarantees. The people who run the systems you depend on know this. The climate scientists know. The financial regulators know. The power grid engineers know. They have read the papers, they have seen the mathematics, and they continue to operate because the alternative is to admit that the systems they are responsible for cannot be made permanently safe, only temporarily resilient, and that the difference between those two things is the difference between the Newtonian premise and the truth. That difference is the distance between 0.506 and 0.506, 127. A fraction of 1 part in 5,000, a rounding error, a cup of coffee, and an entirely different future.